Hello everyone, welcome to my video on implicit differentiation. So up until now we've seen functions that are expressed solely in terms of x, in terms of one variable. This is what we mean by explicit. If the function is expressed explicitly, it's in terms of one variable. So f of x equals x squared times e to the x, or functions such as f of x equals square root of x squared plus 1. These are functions that are expressed solely in terms of one variable. What we mean by the word implicit is that it's written in terms of two variables. So an example would be x squared plus y squared equals 1, the equation of a circle. So notice the difference. Here we have a function written solely in terms of x. Here we have a relation written in terms of x and y. Okay, so another example of this would be something like y plus sine of y equals x. It's written in terms of two variables. We have y and x. Why do we want to look at functions implicitly? Because if you think about it, we could take this first function here, x squared plus y squared equals 1, and just solve for y. We move the x squared over, we have y squared equals 1 minus x squared, then we square root both sides, we get y equals plus minus the square root of 1 minus x squared. So we can express the function this way. But if we look at the second function, so sometimes we are capable of doing this, and then we could derive this using a chain rule, which we know how to do. But if you have a function like this, y plus sine of y equals x, how are you going to isolate y? So implicit differentiation allows us to take the derivative of functions without having to isolate for y. So that's what's nice about it. So let's look at a strategy. How do we solve problems using implicit differentiation? So strategy. First step is take the derivative of both sides of the equation with respect to x. So derive both sides of the equation with respect to x. Okay. So once you take the derivative on both sides, the last step, part 2, isolate for y prime. Depending on the notation you use, if you use the prime notation, that's fine. You could also use the Leibniz notation, dy dx. I'll probably interchange between the two, show you both methods. Both are fine. So this is the strategy. We're just going to take the derivative on both sides with respect to x, and we're going to isolate for y prime. Okay. So in this example here, we're asked to use implicit differentiation to find the derivative of x cubed plus y cubed equals 27. So this is a simple example. Let's just get a feel for it. Let's go ahead and take the derivative. So we write the equation x cubed plus y cubed equals 27. Step 1 of our strategy says to take the derivative on both sides with respect to x. So essentially what we're doing is we're taking this whole thing and we're deriving it with respect to x. So let me use the Leibniz notation to take the derivative of this thing with respect to x, and it's equal to 27, but I'm going to take the derivative of it. So d dx of 27. Okay. Since it's separated by a plus, we could take the derivative of each term individually. So let's go ahead and do that. So we're going to take the derivative of x cubed with respect to x, plus we're going to take the derivative of y cubed with respect to x. And that's equal to the derivative of 27 with respect to x. Okay, so if we look on the right side of the equation, the derivative of 27, we know, I'm saying with respect to x because that's the variable that we're using. Now we're going to emphasize, are we deriving with respect to x, with respect to t, depending on the problems. So here we're deriving with respect to x, and we're going to see why this is important in just a second. But if you're taking the derivative of a constant, our rules still apply. We know that the derivative of a constant is 0. So the right-hand side of the equation is equal to 0. Good. Let's take the derivative of the left side now. If we're taking the derivative of x cubed with respect to x, well, the function's if we focus just on x cubed, this is expressed in terms of x, so this is good. So we just apply our normal power rule. So the derivative of x cubed, we know from the power rule, is just We drop the exponent 3, we rewrite x, and subtract the exponent by 1, so 3x squared. This is done, no problem. Now we're taking the derivative of y with respect to x. And this is where we have to be careful. Since we're taking the derivative of y with respect to x, we don't have an x here, we have a y. So we have to use chain rule, okay? So how would you take the derivative of, let's say, x plus 1 cubed? So if you're taking the derivative of x plus y cubed, let's pretend this is y. Let's assume y is equal to x plus 1. This is just a side example just to get an understanding of the concept. To take the derivative of x plus 1, which we'll call y cubed, what you're going to do, or what we've seen in past videos, is we're going to apply chain rule. We're dropping the 3, we're recopying what's inside, subtracting the exponent by 1, and then we're multiplying by the derivative of what's on the inside. But now we don't have x plus 1, we have a y. But we're going to use the same concept, the same idea. This whole term here, we could just substitute it with y and use the same argument. So y cubed becomes 3y squared times y prime. Every time we had an x plus 1, you're essentially replacing it with y. And this is what we get here. So every time you're using implicit differentiation and you're taking the derivative of y with respect to x, by chain rule, we're going to have a y prime that comes out, or a dy dx, depending on the notation that you're using. Okay, so the derivative of y cubed, we think of it as an x, so we drop the 3. We don't write x, we write what we actually have, which is a y squared. Then we multiply by y prime, or dy dx. Let me use dy dx just to stay consistent with the notation that I'm using here. Typically, I like to use prime notation, but this is fine. We'll use dy dx. Okay. So just keep in mind, every time you're using implicit differentiation, you're taking the derivative of y. This piece is going to appear due to chain rule. Okay. So this is the first step. We took the derivative of on both sides of the equation. Next step is to isolate for dy dx. So all the terms that don't have the dy dx, you bring them on the other side. So we're left with 3y squared dy dx equals, we bring the 3x squared over and it becomes negative, so we get negative 3x squared. And then the last step to isolate the dy dx, it's being multiplied by 3y squared. What do? We divide by the 3y squared. So dy dx equals negative 3x squared over 3y squared. Canceling out the 3's, giving us negative x squared over y squared. And this is the answer. This is our derivative. Okay. So in this example here, we're using implicit differentiation to find the derivative of x to the 4 plus 4xy minus y squared equals 1. Okay. This is a tough example, but try it, pause the video, see if you're able to solve this on your own. Okay. So there's two little tricks that we have to be careful for here. First, and this is very common and you have to catch this, we have x to the 4 plus 4xy. xy, think of it as x times y. Okay, keep in mind, there's a multiplication here, and we're taking the derivative. Something should come to mind. Okay, so we start off by taking the derivative on both sides. Now I'm going to use the prime notation opposed to the Leibniz notation. So I'm just going to put everything in brackets to the exponent. Well, we're going to just write prime equals 1 in brackets prime. So the right hand side of the equation is simple. The derivative of 1, it's a constant, so it's just 0. But the left-hand side becomes a bit more challenging. So we're taking the derivative of this whole thing. The left term, x to the 4, this is simple. We're deriving again with respect to x. So there's no issues here. There's an x. So the derivative of x to the 4, using power rule, we know is 4x cubed. All right? Drop the exponent, subtract the exponent by 1. This is fine. Now we have plus 4xy. I'm going to skip this for now. Give me 2 minutes. I'm going to focus on the last term over here. Let's just do the y squared. So remember, now we're deriving with respect to x, but we're dealing with a y. So what comes out, we're going to take the derivative, it's negative 2y, subtract the exponent by 1, so we get negative 2y. But since we're deriving with respect to x, due to chain rule, we get a y prime that appears. Okay. So this part's done. Now we're doing the challenging part, the 4xy. So I'm going to leave the 4 as is. I'm just going to write down the 4 because it's a constant. Whenever you're taking the derivative of a constant, of a constant multiple, we could just sit them in the front, ignore them, and deal with the x times y. X times y, I'm going to do it here on the side. We're taking the derivative. We have to remember to use product rule. That's the trick here. This is what you have to catch, and this is what students often miss. So be very careful with this one. Taking the derivative of this, let x be the f, let y be the g. So the derivative of the first term x, that's fine. We're deriving x. We're not touching the y. So the derivative of x we know is 1 times y we leave. So we're not deriving it. There's no y prime that appears because we took the derivative of x with respect to x. That's fine. The y, we didn't take the derivative. We just rewrote it. Okay. We're following our product rule. Plus sign. And then we have g prime. So we're taking the derivative of g. X was f. Y was g. Now we're taking the derivative of y. What's the derivative of y with respect to x? Well, the derivative of y is 1, but since we're deriving with respect to x, it's our y prime appears. Okay, and then times f, which we leave. So the derivative of xy, x times y, is y plus xy prime. I'm just going to put the x in the front, and that's our derivative here. So we have 4, I'm going to put it in brackets, y plus xy prime. Okay. Due to chain rule. Well, it's a combination of chain rule and product rule. And now we simplify. So we have 4x cubed plus 4y plus 4xy prime minus 2y times y prime equals 0. Okay, so I essentially just distributed the 4. Next, what we do is all the terms that have a y prime stay on the same side. All the terms that don't have a y prime are moved over, because our goal now is to isolate for the y primes. But what's weird about this example is that we have 2 y primes. How do we deal with this? Well, let's take a look. Move the 4x cubed and the 4y over on the other side because they don't have y primes. So we get 4x y prime minus 2y times y prime equals, we're moving over to 4x cubed on the other side, so it becomes negative 4x cubed, and we're moving over to 4y, so it becomes minus 4y. Okay, and our goal is to get y prime. We want one of them. Here we have 2. How do we go from 2 to 1? Well, to answer that, it's essentially just factoring it out. By factoring out a y prime, we went from having 2 y primes to a single y prime. So if we factor out a y prime, we're left with 4x minus 2y on the left hand side. If you don't believe me, distribute back the y prime and see if it matches what you started with. We get minus 4x cubed minus 4y. And then the last step, to isolate the y prime, we're just going to divide by 4x minus 2y, whatever's left in the bracket. So y prime is equal to negative 4x cubed minus 4y over 4x minus 2y. Okay. And what we could do here is simplify a bit more. On the numerator, we could factor out a negative 4. So if we take out a negative 4, we're left with x cubed plus y. And if we factor out a 2 on the bottom, we get 2x minus y, leaving us with negative 2 on top. Negative 4 divided by 2 is negative 2. So negative 2x cubed plus y over 2x minus y. And this is the final answer. This is our derivative. Okay, so as you can see, implicit differentiation requires practice, especially with this, the product rule. Okay, and remember, whenever you're taking the derivative of a term that has a y in it, because of chain rule, we get a y prime that appears. So in this example here, we're asked to find the equation of a tangent line of a lemniscate at the point negative 3 and 1. So a lemniscate, the equation of a lemniscate is 2 open bracket x squared plus y squared close bracket squared equals 25 open bracket x squared minus y squared close bracket. So a lemniscate is essentially the infinity symbol. So that's what I graphed over here. Notice that it's not a function because it fails the vertical line test. And we're looking for the equation of a tangent line at the point negative 3 and 1. So the point negative 3 and 1 ends up being around here, somewhere in the second quadrant. That's the point negative 3 and 1. And we want the equation of a tangent line. So a tangent line is a straight line that hits the function at that single point. So it's going to look something like this. So I'm expecting the slope to be positive, and this is our goal. Our job is to find the equation of this line here. So let's go ahead and do that. So let's begin by reminding ourselves that the equation of a tangent line is f prime of a times x minus a plus f of a. So f of a is given. We know that a is -3 and f of a is 1. So this part here is done and this part here is given. What we have to do is go ahead and find f prime of a, the derivative, and then substitute, once we find the derivative, substitute our values in. So let's go ahead and do that. So since it's given to us implicitly, let's take the derivative with respect to x on both sides of the equation. I'm going to use the prime notation, all this prime, all this prime. So the 2 in the front doesn't bother us. Let's start off with the left-hand side. We'll rewrite 2 because it's just a constant multiple. So taking the derivative of a constant multiple, we can leave it in the front. But what we have to deal with is the x squared plus y squared, all that squared. Okay. One way of doing this is rewriting x squared plus y squared and squaring it. So it's a binomial, so we could essentially distribute and FOIL and then solve it that way. Not the most efficient way, I wouldn't do it this way. The better way to do it is to use chain rule. So if we apply chain rule here, we start off by dropping off the 2. So on top of this 2 here from the front, we're going to drop the exponent 2. We're going to leave what's in the inside, x squared plus y squared. And then we subtract the exponent here by 1, so we're left with 1. I'm not going to write it. And then we take the derivative of the inside. So we're multiplying by the derivative of the inside. So times, I'm going to open bracket. To derive the inside, we're starting with the x squared. So the derivative of x squared with respect to x, just normal power rule, so 2x. And then the derivative of y squared with respect to x, we get plus the derivative of 2y is just, y squared is 2y. And then because we're deriving y with respect to x, we have to multiply by y prime. Okay. And this is equal to the right side. I'm just going to distribute the 25 before I derive. So I didn't take the derivative yet. I'm just going to write it as 25x squared and then distribute minus 25y squared. And we're going to leave the prime notation here. So over here, what we're left with on the left side is 4x squared plus y squared, 2x plus 2y times y prime. And that's equal to, on the left-hand side, let's take the derivative now. We're going to take the derivative with respect to x of 25x squared. Dropping the exponent, we get 50x. Since we're deriving with respect to x, and this term only has an x, we don't have to multiply by y prime. The next term is minus 25y squared. We're deriving that term with respect to x, so we're going to have to multiply by y prime. So the derivative of negative 25y squared, we treat it like an x, and we get negative 50y. And then because we're deriving with respect to x, multiply by y prime, thanks to chain rule. Okay. So now what we have to do is we have to isolate y prime. So the issue with the y prime here is that it's trapped into the bracket. We have to remove it from the bracket. In order to do that, we have to distribute. We have no choice. Okay. So let's go ahead and do that. So I'm going to leave the 4 on the outside, and on the inside we're just going to distribute. So x squared times 2x cubed, x squared times 2y times y prime. We get plus 2x squared y times y prime. Now y squared times 2x, you get plus 2xy squared, and then y squared times 2y times y prime, you get 2y cubed times y prime, equal to 50x minus 50y y prime. Okay. At this stage, we could distribute the 4. So multiplying everything here by 4, I'm just going to do it over here. So 2 times 4 is 8. Multiplying this by 4, we get 8. Multiplying this by 4, we get 8. And multiplying this by 4, we get 8. So I just distributed the 4 that was sitting in the front to all the terms. Okay. Now what we do is all the terms that have a y prime, we put on one side. All the terms that don't have y primes on the other side. So this is going to stay. This is going to stay on the left side. And we're going to move this guy over on the right side because that's a y prime. At the same time, I'm going to take the 8x cubed, move it on the right side. The 8xy squared, we're going to move it on the right side and leave the 50x on the right side. This gives us 50y y prime plus 8x squared y prime plus 8y cubed y prime. Notice you cannot combine the y with the y prime, not the same terms, so be careful with that. Leave the y primes on their own. And on the right hand side, what we get is 50x minus 8x cubed, and then minus 8xy squared. Okay. At this stage here, we're going to factor out a y prime, leaving us with 50y plus 8x squared y plus 8y cubed, and that's equal to 50x minus 8x cubed minus 8xy squared. Okay, and then the last step is take this whole thing and divide it over here. So I'm running out of room. I'm just gonna go ahead, erase all this, and divide it down here. So this whole term divided by 50y plus 8x squared y plus 8y cubed. Okay, so I took this whole term here. It's multiplying the y prime. We're just gonna divide it. This gives us y prime. Okay. And now our goal is to evaluate it at this point. So we found the derivative, but we have to find the slope, we have to evaluate it at the given point. Notice that here there's x's and y's. So we have to use our x and y point that's here. So substitute all the x's in our slope, and in our derivative with -3, and substitute all the y's in our derivative with +1. And that's going to give us the slope of the tangent line. So let's go ahead and do that. I'm just going to erase to give myself some room. So the notation that's used to evaluate a point, so it's y prime, and we use this dash to say that we're going to evaluate the derivative of y prime at -3 and 1. Okay, so we're going to substitute all the x's with -3, all the ones with y. All the y's with 1. So this gives us 50 times -3 minus 8 -3 cubed minus 8 times 1 times, 8 times -3 times 1 squared. All this divided by 50 times 1 plus 8 times -3 squared times 1 plus 8 times 1 cubed. Okay, so all the x's were replaced with -3, all the y's were replaced with 1's. Just gonna erase this. And now we evaluate this. So let me use a calculator. What we get is -150. This is going to become positive. 3 times 27 times 8. We get 216. This is 1. This is plus 24. Over on the bottom we have 50. Here we get -3 squared, which is 9. 9 times 8 is 72. And plus 8. Giving us, what is this? -150 plus 216 plus 24. We get 90 on top. On the bottom, 72 plus 8 is 80 plus 50. We get 130. The zeros cancel. 9/13. Okay, so this is the slope, and as we expected, our slope was going to be a positive value from our drawing. Okay, so the fact that I got a positive answer is reassuring. Next, let's go find the entire equation of a tangent line. Okay. So if it asks for the slope of the tangent line, we're done. The answer is 9/13. But if it asks for the equation of a tangent line, we plug it into this formula. So the equation of the tangent line is f prime of a. Let's just recopy the equation. X minus a plus f of a, giving us t of a. F prime of a is essentially the slope, which we got is 9/13. x minus a, our a is negative 3, so it becomes x plus 3. And our f of a is our y plus 1. And this is the equation of this tangent line. Okay. Good. So in this example over here, it's asking us to find the second derivative given the function x to the 5 minus y to the 5 equals 5. So it's given to us implicitly. So notice how we're combining two different notions. We're combining the notion of implicit differentiation along with higher derivatives. But let's go ahead and do it. So we know how to find the first derivative. Let's start off with that. We'll use Leibniz notation to take the derivative with respect to x of x to the 5 minus y to the 5 and show that it's equal to the derivative of 5. So the right hand side of the equation is simple. The derivative of 5, a constant, is just 0. That's okay. Left hand side, not too difficult. The derivative of x to the 5 with respect to x is just power rule, 5x to the 4. That's simple, but here we're taking the derivative of y with respect to x. Again, we're invoking chain rule. So we get minus 5y to the 4. And since we're deriving a y prime appears. Okay. Now our goal is to find the y prime, giving us, we'll move this over, leaving us with 5x to the 4 equals to positive 5y to the 4 times y prime. Okay, so I moved this whole term over. And next, isolating the y prime, we're just going to divide both sides by 5y to the 4. This gives us y prime is equal to the 5's cancel, leaving us with x to the 4 over y to the 4. Okay. So that's the first part. We found the first derivative. Let's go ahead and find the second derivative. How do we do that? We're going to take the derivative of this. Okay. Notice how we have a fraction, so we're going to have to use quotient rule. Let's go ahead and do that. So this is the first derivative. This is the answer. And now let's go get the second derivative. So in order to do this, we're going to do x to the 4 over y to the 4, all that prime, using quotient rule, which, let me remind us up here. Quotient rule, if we have a division of two functions, we take the derivative of the top times the bottom minus the derivative of the bottom times the top, all that over g squared. So the derivative of the top is just 4x cubed times the bottom we leave, y to the 4. Notice there's no y prime because I didn't derive the bottom, we just left the bottom. We took the derivative of the top, the x to the 4, giving us 4x cubed, but the bottom we didn't derive, okay? We just rewrote it, following our rule. At this step, after the minus, now we have to take the derivative of the bottom, and we're deriving again with respect to x. This is a y, so when we take the derivative here, we have to remember to multiply by y prime. Okay, so this is what you have to catch, and then multiply it by x to the 4, finishing off our quotient rule, and that divided by y to the 4, all that squared. Okay. So now to simplify this, what we have is we could replace the y prime over here, because we don't want a y prime in the equation, with what it's equal to. So we know y prime is equal to x to the 4 over y to the 4 that we saw earlier. So this gives us 4x cubed times y to the 4 minus 4x to the 4 y to the 3 times y prime, which is x to the 4 over y to the 4. All this divided by y to the 4 squared is just y to the 8. Let's keep going. On the top, we could cancel out. We have a y cubed here and a y to the 4. So if we have 3 of them on top, we cancel with 4. So we're left with 1 on the bottom. This gives us 4x cubed times y to the 4 minus 4 x to the 4 times x to the 4, that's x to the 8 over y. All this over y to the 8. Okay. Now what we could do is on the numerator we have a fraction minus a fraction. We can find the common denominator. So essentially we're going to multiply the top and the bottom by y, giving us 4x cubed times y to the 5, because we're going to multiply this by y, minus 4x to the 8, all this over y. All this over y to the 8 over 1. Y to the 8, think of it as y to the 8 over 1, and we're going to flip it, giving us multiply, because this is a fraction, you're dividing fractions. Let's make this bigger to emphasize. Fraction divided by a fraction, we're going to flip this one, giving us 4x cubed y to the 5 minus 4x to the 8. All this over y, but then this could be y to the 8, it's going to be flipped, giving us y to the 9. Okay. So notice that y to the 8 over 1 becomes 1 over y to the 8, and since we have y to the 8 and y to the 1, 1 plus 8 is 9, giving us y to the 9. This is good enough, but we could go further. On the numerator, we could factor out a 4, and we could factor out an x cubed, giving us 4x cubed over y to the 9 times, if we factor out a 4x cubed on top, we're left with y to the 5, and if we factor out a 4x to the cubed from the 4x to the 8, we get minus x to the 5. Okay, and we could actually simplify this further, because what's y to the 5 minus x to the 5? Well, going back to the initial equation that we started with, x to the 5 up here, x to the 5 minus y to the 5. Notice that it's in the reverse order, so we could just multiply both sides by -1. This is just equal to -5. Right? If you multiply this by -1 and -1, we get y to the 5 minus x to the 5. Or in a sense, you could just bring all this over to this side and bring the 5 over on the other side, and you get the same thing. So if this is equal to -5, the simplified answer is -5 times 4 is -20, x cubed over y to the 9. And that's the answer.